Hey, appreciate it, Joe. Let's see. Thanks, everybody. Looks like we're on the last day of things, and I'm going to talk about some exploration I've been doing with a particular code on the AWS systems that have deployed some ARM architecture. Um, well, the motivation behind this whole exploration of using the Nalu code is the fact that I really would like to do this exploration with mission critical codes at Sandia, but that's just not possible. So not so much a proxy code, but an actual true comparative code that is open sourced for the world to use is Nalu. And it has quite a complicated code structure and infrastructure when you think about all of the underlying code sets that exist under Nalu that do comprise what is known as the Sierra toolkit that's available at Sandia, Los Alamos, and our TriLab friend, Lawrence Livermore. Yeah. So the whole point of this exploration is to understand how Nalu and furthermore, possibly Spark would perform on different types of ARM architecture. And AWS offers some nice comparative ARM platforms and possibly more in the future. So this presentation is going as a quick outline is I'm going to propose a process on how to do fair comparisons between different architectures. And then I'm going to show you what Nalu is made up of, and particularly what experiment I'm using. And then I will show you the results themselves, particularly scaling results, and declare what the differences are with regards to the actual microarchitectures that I'm comparing. Then I'll follow up with a proposed plan to diagnose the performance differences we see across the architectures and conclude with some future work that is actually happening right now. All right. So for fair comparisons, one of the things that we've been thinking about when we try to compare different type of platforms, microarchitectures, and their performance is, do we actually start off with the exact same software stack on the different platforms? Baseline to even think about having an apples to apples comparison. So it's this notion of provenance when it comes to an actual software stack. Secondly, you need to worry about, well, are you building it in as much of the same way on the different microarchitectures, and are you running it in similar ways to make a fair comparison? And I bullet here that this also can challenge your productivity, but it's something that needs to be considered. And how do you track what kind of compilers, what kind of versions of softwares, build flags, and so forth that you're using in order to do these comparisons? So the solution that we've iterated toward is the use of SPAC. And hopefully the community is familiar with SPAC when it comes to high performance computing applications. It's definitely getting a lot of traction, and the more the community grows, the more robust SPAC is going to be. So my usage of SPAC for this type of comparison and future performance engineering effort is, one, I make sure that I'm using the same hash of the development branch of SPAC when I do these builds across all platforms. And the second bullet, you see SPAC install Nalu, so forth, so on in red, is literally the command I typed on different ARM x86 and ARM instance at AWS with no other commands whatsoever. I literally fired up instances, of course, upgraded the instances with regards to their OS, and then cloned SPAC, and I typed in that command and things started happening. The particular hash is listed here for people's future reference. And the results you're going to see are not with the results where I did not do any microarchitectural optimization. I did not specify particularities of flags with regards to compilers, knowing the architecture I was on. I just used what was out of the box with SPAC and almost like a push button fashion to establish a baseline. So jumping over to what is Nalu. So Nalu is a CFD code primarily stewarded out of Sandia. And in this case, it's a low Mach number CFD code. It has a lot of the same infrastructure as Spark and higher Mach number resolving CFD codes that our Trilabs are use in mission critical fashions. The dependencies of HDFI, PNet, CDF, Trilinos, Cocos, these packages that I'm speaking of actually have to be built on the different platforms in as much of a similar fashion as possible. Thus, using SPAC allows for that to happen almost seamlessly. So Sandia itself, Nalu itself, it's a massively parallel computational code. The variable density solve is pretty impressive for such a code. And the fact that it does the predictions of aerodynamics and gas phase gas phase combustion is, you can imagine, a very detailed simulation of a jet flow from an actual combustion jet. Another application that I've seen Nalu used for is aerodynamic flow around a projectile going through an atmosphere. On the right column, I have the particularities of this experiment that I'm using. So in a milestone case at the labs, there is what is known as the R3C NT case, which is a 17 million element, finite element resolved case that is the jet flow around a cone that is shown in the right image. And we have more details about the particular problem. Trilinos is being used to solve the actual equations. And in this case, Cocos is dealing with all the data and memory management and decomposition per node. For this experiment, I used only OpenMPI, no proprietary MPIs, and the OpenMPI was built directly from SPAC. Here we have a comparison of the actual instances that I used on AWS. So C5N versus C6G. So whenever I say C5 versus C6, C5, think of x86, particularly Skylake, 18 cores per socket with 2 threads running at 3 gigahertz. And when I say C6, think of an ARM chip running 64 cores, 1 thread per core, slightly slower clock speed. Now, mind you, the networking performance, the network performance between the x86 and the ARM instances, they differ only when I'm using a C6 instance versus a C6GN instance, where I highlight in red, and I tried to my best to kind of make an easy identification. Everything dealing with C6GN that's particular to that is written in red. Therefore, you see a difference of 25 to 100 gigabit with regard to the network. And at the very bottom, where the row displays what the price per hour per node is, and these are in dollars, there's a difference. So as we proceed, or if you do plan to use the Amazon system, you can think of C5N.18x large and C6GN.16x large as your most comparative clusters that you want to spin up. And The bottom link is available for everybody. Just click on that, and that'll take you directly to the pricing systems for AWS Linux using a Linux OS, the AWS Linux OS, and this is the on-demand pricing. So this is when you just are going to spin it up and you haven't previously reserved or time on their systems or have done any type of other speculation. So moving on to actual scaling results of the code. This is the first time I've actually been able to run this code at 100 nodes on the system. So we have from 2 nodes to 100 nodes, we have a speed up comparison where yellow is x86, green is the standard OFI networking fabric interface for OpenMPI. And then the orange is using the AWS's proprietary EFA, Elastic Fabric Adapter, for their interface. Particulars to notice is I had to start with 2 nodes as my smallest collection of instances because that is the smallest size of a cluster that can actually hold the problem in memory and run to completion. And in this case, completion is only 25 iterations. So it's just it's going through the initial phase of actually spinning up the fluid flow around out of the jet flow. Then as we increase the number of nodes, we have a scaling comparison between the 3 platforms until we get to 64 nodes and 100 nodes. The reason why I don't have C6GN data displayed here is because in creating these parallel clusters, you can be challenged by a cap of what is allowed by your account in regards to how many cores and instances you can actually deploy at once. And I butted up against that issue on this particular instance of C6GN. That's going to be resolved hopefully soon so that we can get up to much larger problems. But as you see speed up happening, though it's not optimal, you are seeing speed up all the way up to 100 nodes and possibly even further, which one identifies that the problem size is large enough to actually be parallel or be decomposed in a parallel fashion such that you can achieve speed up. Secondly, the trend I'm inferring from the trend that I can actually go to a much larger node count and still see some speed up. While this process was happening, some things that I noticed was the decomposition that I was following, the rubric I was following for smaller node count did not offer the best timings when I got to larger node counts, such as full nodal saturation with MPI ranks versus any OpenMP threads at smaller node counts is not the case at larger node counts. And that can be the case when you start to observe backend stalls on different architectures. So a lot of room of exploration to start diving into, but that was an initial observation. Another thing to consider when you're dealing with these systems, which I think a lot of people have interest, is the actual cost of a simulation. In this case, just 25 iterations, but still, it's a reasonable thing to do to look at what the cost is. So here is a comparison of cost for those 25 iterations on different node counts. And you're seeing the vertical scale is in dollars. So across the board, you're definitely seeing the ARM architecture being offered as a cheaper solution. So not only are you getting to your solution more quickly than an x86 system that Amazon is offering as their HPC solution, you're also getting into the solution with a less of a cost. Right now, in this unoptimized configuration, I'm seeing that the non-EFA enabled clusters are the best solution per dollar to get to this 25 iteration count mark. I'm sure this numbers will change when we actually start to get more and more optimized runs. And in the process of getting more optimized runs, the mandate of our team, myself and a member of AWS, Steve Messenger, is to take our optimization recipes and feed them back into via pull requests to SPAC to offer it up for the rest of the community to use. So hopefully everybody else will be able to use the recipes on the AWS systems with a considerable amount of savings. And they can use it as guides for their own applications. So when one wants to actually look at what the possibility of differences between these different platforms, I started to use a profiler called MAP and its capability of just creating a splash page performance report. Mind you that all of the metrics that are being used with regards to performance are coming straight from a Linux perf and nothing more. Here you have 2 pages of a display of these very high level performance differences that are being observed at the 100 node count. If you carefully look at these, I believe this has been recorded and the slides are going to be saved so you can go back and scrutinize the data that's on these 2 pages. You have 100 ranks or 100 processors, which actually is 100 ranks versus 800 ranks for the C6 C6Ns. Sorry, that should be C6G versus the C5Ns. And you have 900 processes for the C5Ns. Yes, different number of processes per rank, but the nodal count's still the same and the dollar count is still the same. The time to solution is different. You make the judge as to what's most important to you. I think dollars are. So then you have possibilities of why you have differences. You can see that the compute fairly the same, MPI fairly the same in terms of the total overall percentages of simulation time. But then you have, and then you have, a comparison of CPU metrics, and then you have it's noted. Please note that CPU metrics on the different CPUs, be it x86 and ARM Arch, are presented to perf in different, I guess, the different ideas of categorization. So what's available on the 2 are different architectures make it difficult, but not impossible to do true comparisons. Vectorization, memory access, that's usually categorized in the same fashion. But when it comes to things like back-end stalls and front-end stalls, that's more available and is going to be even more available for ARM architecture according to current and future roadmaps. So this type of high-level comparison between these 2 platforms can be done quite easily with a tool like MAP. And that is what is going to be necessary to actually tease out what are the optimal configurations, both with decomposition, algorithmic challenges, not so much with compiler flags themselves, but we're going to have to use a profiling tool such as MAP or TAO on these different platforms in order to understand what are the possible optimal ways to run these codes and hopefully propagate that information back to some of the mission critical codes that are at our national labs. Here we have an example of map on an earlier investigation I did of a smaller sized problem of 4 nodes on M6G, which is quite similar to the C6Gs, which is still the same Graviton 2 chip that's available at Amazon. It just has a higher DRAM availability on those nodes. So in conclusion, as more ARM-based systems are being available for the community to use, we're doing some profiling analysis. And mind you, all these results are coming about just by using the SPAC right out of the box. Let's see. Using SPAC allows for software management, which allows for provenance with regards to code use, and establishing a baseline for comparisons and configurations. Some things that I think people are going to be really interested in is future ARM architectures that hopefully will be available on AWS and these different type of cloud services. Excuse me. And with SPAC, we're going to be introducing more and more micro-architectural optimizations into the code management system, and offering up more and more recipes for different compilers. I didn't mention, in this case, if you saw that line from SPAC and you're familiar with it, all the results you saw on the different microarchitectures is using GCC 10.2. And there is other available compilers to be used on the different architectures that I think would be offer more insight as to what is the possible performance. So with that, I will conclude with some references, and I don't know if I should go ahead and probably stop sharing to answer your questions. Joe?